Section 2.2, describing sets. So I'm going to let you read this quote from the Common Core Standards for Mathematical Practice. Basically, it's telling us that students need to be able to understand sets. And so you need to understand sets as well. Greg Cantor first created set theory in 1871 through 1884. And his research has had a profound effect on research and mathematical teaching. Sets and the relationships between sets are the basis for teaching kids the concept of whole numbers and less than, as well as addition, subtraction, and multiplication of whole numbers. Think about a 3-year-old. If you place, say, 3 blocks in front of them and ask how many objects are in this set, what happens if I take one away? So sets are really going to be the foundation of us getting started with mathematical thinking. So what is a set? A set is any group or collection of objects. The objects that are in your set are called the elements or members of the set. And so one way that we denote a set is just to list the elements inside these curly braces. And we do use these curly braces that you see here to denote that what's inside these braces is what's in the set. So this is called the roster or listing method. Here we have the set A equal to 1, 2, 3, 4, 5. So for example, 1 is an element of the set A. 6 is not an element of the set A. All right, so I want you to think about what is the set of vowels in the American alphabet. I'll let you think about that. Go ahead and pause the video and write it down yourself. Okay, so you should have paused and written it down yourself. What are the vowels? Well, our vowels are A, E, I, O, and U. So that is the set of vowels in the American alphabet. All right, so let's talk a little bit about sets. Every element of a set is listed only once. So if 1 is in my set, I only need to list it once. I don't need to list it more than once. The order of the elements is unimportant. So that set A that was 1, 2, 3, 4, 5 is the same as the set 3, 1, 2, 5, 4. So it doesn't matter what order I list those elements in. We say that an element is in the set A using this funny looking E symbol. So I would say, for example, that 1 is an element of A. And we use that funny looking symbol with a line through it to say that something is not, in the set. So going back here, 6, remember, we said was not an element of A. For example, when we're looking at the vowels, A is an element of V, the set of vowels, but B is not. Your set has to be well defined. So given an object, you should be able to decide, is this object in the set or not? Here are some more sets that are described using the roster or listing method. So C is the set of colors that are red, green, yellow, or blue. N is the set of natural numbers. So the natural numbers are sometimes called the counting numbers, starting with 1. So 1, 2, 3, 4, 5, 6, and so on. These ellipses here are telling you that you just keep going in that pattern. Same idea with the lowercase letters. L is the set A, B, C, D, E, F, G, all the way through Z in this case. Now notice here the natural numbers goes on for infinity, right? There's always another natural number. The set L is still finite. It'll end after we hit Z. Okay, so here's another way of denoting a set. This is called set builder notation. What this notation does is it tells you how to determine what the elements of the set are. So we're going to read it from left to right. E is the set of all elements X. This bar is telling me such that X is an element of the natural numbers and X is less than 11. Okay, so that's how we would read this. Now, given that information, you could list out everything that is in E. So I need things in E must be natural numbers and less than 11. So what are the natural numbers that are less than 11? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. All right, so let's try working the other way. Here are some sets that have been described using the listing method. Let's use set builder notation to describe these sets. So let's start with A. And let's give this a name. Let's call it capital A. Well, what do you notice about the elements of capital A? We have 2, 4, 6, 8, 10. They're all even, right? So we're just picking up the even natural numbers. So, well, one way to describe that is just to write it in words. A is the set of little a such that A is an even natural number. But let's try to use some more notation to describe this. So again, I want A to be the set of little a. Well, how did we do it on the last slide? We said that little a was a natural number. This little line in front of the n is just telling me that this is the natural numbers. And A is even. Well, let's think about that a little bit more. What does it mean for a number to be even? Well, it has to be divisible by 2. So you have to be able to write it as 2 times a natural number. So I could say that A is the set of little a such that A equals 2n, where n is a natural number. And finally, I could clean this up a little bit by just saying A is the set of elements that look like 2n such that n is a natural number. Okay. And you notice this last line is a lot more concise than what we started with. All of these are acceptable answers using the set builder notation, but this last answer is what we're aiming for, something that's a little more concise but still explains what we're looking for in our set A. I'm going to let you do the odd numbers, this set B, on your own, and I'll collect that for homework. All right, here are some sets that are described using the set builder notation, and we want to now write them using the roster method. So let's look at set A. Set A is the set of elements that looks like 2k plus 1 such that k is equal to 3, 4, or 5. Well, let's calculate 2 times 3 plus 1. So that's when k is 1. That's going to give me 6 plus, I'm sorry, k is 3. That's going to give me 6 plus 1, which is 7. What about 2 times 4 plus 1? That's going to give me 8 plus 1, which is 9. And finally, 2 times 5 plus 1 is going to give me 10 plus 1, which is 11. So these are all the possible values for elements of A. So A is the set containing 7, 9, and 11. All right, you should pause the video and try B and C on your own. And when you've got an answer down, hit play again and check that your answer matches mine. All right, so B is the set of elements that look like 5k minus 4, where k is less than 10 and k is a natural number. So what are the possible values of k? Well, they have to be natural numbers that are less than 10. That's 1, 2, 3, 4, all the way up to 9. So I need to calculate 5k minus 4 for all of those values. So 5 times 1 minus 4 is going to give me 1. 5 times 2 minus 4 is 10 minus 4, which is 6. 5 times 3 minus 4 is 15 minus 4, which is 11. 5 times 4 minus 4 is 20 minus 4, which is 16. Whoops. Erase that. How about 5 times 5 minus 4? That's going to give me 21. 5 times 6 minus 4 is going to give me 30 minus 4, which is 26. 5 times 7 minus 4 is 35 minus 4, which is 31. Whoops. 3. 5 times 8 minus 4 is going to give me 36. There's my 3. And 5 times 9, let's squeeze it in, minus 4. That's going to give me 45 minus 4, which is 41. All right, so here are all my elements of B. So B is the set containing 1, 6, 11, 16, 21, 26, 31, 36, and 41. How about C? C is the set of X such that X is a positive, even, natural number less than 8. So I just need to list out the positive, even, natural numbers less than 8. I've got 2, 4, 6, and 8 is equal to 8, so that's not less than 8. So there we go. Two sets are considered equal if and only if they contain the same elements. The order of the elements makes no difference. If two sets are equal, we write A equals B with the equal sign. If A is equal to set B, then every element of set A is contained in set B and vice versa. Every element of set B is contained in set A. If set A is not equal to set B, then there has to be at least one element that is not contained in both sets A and B. All right, so let's look at some sets. A is the set 1, 2, 3, 4. B is the set 4, 5, 6, 7. C is the set of X such that X is a natural number greater than 3. And D is the set of X such that X is less than 4 and X is a natural number. Which, if any, of these sets are equal? Again, please pause the video and try this on your own, and then you can unpause and look at my answer to make sure it matches with yours. Okay, if you're having trouble getting started, let's start by writing out the elements of C and D, because those are in set builder notation. But if I'm comparing two sets, it's easier to have the elements listed out. So C is the set of X such that X is a natural number greater than 3. So it has to start greater than 3. So 4 is going to be in C, then 5, 6, and that's just going to keep going, right? So dot, dot, dot. What about D? D is the set of X such that X is less than 4 and X is a natural number. So what are the natural numbers less than 4? I've got 1, 2, and 3. All right, so here are my 4 sets. Are any of them equal? The answer here is no. If you look at all of these sets, none of them have the same set of elements in two sets at the same time. We certainly have some containment. So for example, if you look at set D, D is the set containing 1, 2, 3, and that set, those elements are all contained in set A, but D doesn't have the element 4, which A has. Okay, so here none of the sets are equal. If we compare elements from the sets P and S such that for every element of P, there's exactly one element of S and vice versa, then we say the two sets P and S are in a one-to-one correspondence. So for example, I can put set 1, 2, 3 in a one-to-one correspondence with set ABC by the following. I'm going to pair 1 with A. Let's see. There we go. Pair 1 with A, 2 with B, and 3 with C, and vice versa. Or I could pair 3 with A and 2 with B and 1 with C. These aren't the only ways that I could build a one-to-one correspondence between these two sets. So I want to list out all the possible ways of doing that. And so one way to help me organize my thoughts here is to use something called a tree. Another way is to use a table. So we'll look at both here. So if I use the table, across the top here, I have the elements of my first set, 1, 2, and 3. And in each row, I have a possible correspondence. So that first row is the correspondence that 1 is associated with A, 2 is associated with B, and 3 is associated with C. Okay. And so really all it amounts to is how can I list the elements A, B, C in order, right? How many ways could I order those? Using the tree here, I'm going to list my elements of the first set up here, and then I'm going to think about defining my correspondence one element at a time. So if I start with 1, what are the possibilities of elements that I could associate with 1? Well, I haven't assigned anything yet, so I could associate 1 with A, or with B, or with C. So I have 3 possibilities here. Now, once I've assigned, say, 1 to A, when I go to assign something to 2, I can no longer use A. So for 2, I could assign 2 to B or 2 to C. And similarly, if I had chosen B for 1, then I could assign 2 to A or to C, but not to B. And finally, when I move on to 3, well, I've already assigned the first 2 elements. There's only 1 element left in my second set. And so that decision is determined by my previous choices. Okay. And now if I want to figure out how many correspondences there are, I just look to see how many paths are there in my tree. So there's 1 path, there's a second path, there's a third, fourth, 5th, and 6th. So there are 6 correspondents, and if I needed to list those correspondences out, I would just do the assignment based on my tree. Okay. Oops. There we go. All right, so the question is, how could I determine how many one-to-one correspondences there are between 2 sets? Well, we're going to use something called the fundamental counting principle. This says if I can perform event M in M ways, and after that I can do event N in little n ways, then performing event M followed by event N takes M times N ways. So for example, to determine the number of one-to-one correspondences between 1, 2, 3, and ABC, I'm going to think of my events here as assigning an element to each of the elements of my first set. So when I go to assign 1, think about our tree. I had 3 choices for assigning 1. I could assign it to A, B, or C. Now when I move to assign 2, I've already chosen an element from ABC to associate with 1, so I'm down an element, so I have 2 choices for assigning 2. And finally, when I assign 3, I have 1 choice. There's only 1 element left that hasn't been assigned. Now, the fundamental counting principle says if I want to assign all 3 of those elements, the number of ways to do that is found by multiplying each of these numbers here. So I have 3 times 2 times 1, which is 6 ways. Okay, so there are 6 one-to-one correspondences between 1, 2, 3, and ABC. All right, let's try another example. How many one-to-one correspondences are there between the sets 1, 2, 3, 4, 5, and E, F, G, H, I. So let's do the same thing. I want to break it down into tasks. So I'm going to assign 1. And I'm going to stop writing assign and then just write the number. So assign 2, assign 3, then I've got to assign element 4 and element 5. Okay, so when I start with element 1, there are 5 choices of what I could assign it to. So there are 5 ways I could assign element 1. And now I've taken one of those choices out. So when I go to assign 2, I'm down to 4 choices. For 3, I have 3 choices. For 4, I have 2 choices. And for 5, I have 1 choice. The fundamental counting principle says I need to multiply these to get the total number of ways to assign a correspondence between these two sets. So 5 times 4 is 20. 3 times 2 is 6. 20 times 6 is going to give me 120. What about correspondences between the same two sets where 1 is mapped to F? Well, I'm going to have the same start here, so I need to assign 1 and 2, 3, 4, 5. But when I go to assign 1, I only have 1 choice. It goes to F, right? This is the only way I'm going to map 1. Now when I go to assign 2, F is out, so there are 4 choices left. There are 3 choices for 3. There'll be 2 choices for 4 and 1 choice for 5. So when I multiply these together, I get 4 times 3 times 2. That's 12 times 2 is 24. So there are 24 correspondences where 1 is mapped to F. All right, now I'm going to fix 2 elements. So F is going to correspond to 1 and I is going to correspond to 2. So again, think of my tasks as assigning each of the elements in my first set. 1 maps to F, so I have 1 choice for 1, it maps to F. 2 maps to I, so I also have 1 choice for 2. Now F and I have been assigned, so there are 3 elements left I can choose from for 3. And once I assign one of those to 3, there'll be 2 elements left to choose from for 4 and 1 element left for 5. Again, the fundamental counting principle tells me to multiply each of these, and so I get 6 possible ways of assigning those. All right, finally, let's look at one-to-one correspondences between the sets 1, 2, 3, 4 and E, F, G, H, I. Well, let's take a second here and look at these two sets. There are 4 elements in the first set and 5 elements in the second set. Remember, one of our conditions for having a one-to-one correspondence is that every element of the first set corresponds to 1 element of the second set and vice versa. Well, if I try to set up a correspondence here, so let's just think about a sample correspondence, E, F, G, H, I. I could correspond 1 with E, 2 with F, 3 with G, and 4 with H, but the problem is I've got this I left over with no one up above to correspond to I. This means I can't create a one-to-one correspondence between these two sets. They don't have the same cardinality or the same size. Okay, so the answer here is 0. It's not possible to get a one-to-one correspondence between these two sets. All right, so we're going to call 2 sets equivalent, and we use a little tilde, so A is equivalent to B, if there is a one-to-one correspondence between the sets. So if 2 sets are equal, they have exactly the same elements. If 2 sets are equivalent, they don't have the same elements, but we can find a one-to-one correspondence between the 2 sets. All right, I want you to look at this example and determine which of these sets are equal and which are equivalent. This is one that I'll collect from you as homework.